All right, let's dive right in. Today, we are going to try something pretty wild. We're going to decompile reality itself. We're going to look at the universe not as a collection of things, but as a running program. And by looking at it this way, we're going to tackle one of the deepest, most difficult problems in all of mathematics.
So first, I want you to just think about this question. Is the universe made of things, or is it made of actions? I mean, look around you right now. You see objects, right? Tables, chairs, people, what we call nouns. But what if that's just a sliver of the picture? What if the real reality isn't the thing itself, but the process that keeps it there? What if the universe is fundamentally made of verbs?
This right here, this is the new rule for reality we're exploring today. The idea is that the universe is this constantly unfolding dynamic process. It's a verb. In our act of observing it, of just looking at it, it kind of freezes a single frame of that process. And that snapshot is what we perceive as a solid, stable object, a noun.
Okay, so to really get our heads around this, we've got to be clear on what we mean. What's a verb and what's a noun when we're talking about the operating system of the entire universe?
It's pretty simple when you break it down. A verb is the process that's running. It's the dynamic flow of energy. It's the wave moving through a field. The noun, on the other hand, that's what we get when we measure it. It's the frozen state, the stable pattern we see, the particle we detect in one specific spot. See, they aren't two different things. They're just two faces of the exact same reality. One is in motion, and the other is how it looks when we hit pause.
So how does this magic trick happen? How does a verb become a noun? Well, the mechanism is called projection, and it's driven by the simple act of observation. When we look at some incredibly complex, higher-dimensional process from our limited, fixed point of view, we essentially collapse all that dynamic weirdness into a simple, static object.
This is the perfect way to picture it. Imagine a spiral, like a spring, spinning in 3 dimensions. That's the verb. It's moving, it has depth, it's a whole process happening over time. But if you look at it straight on from the end, what do you see? You just see a flat 2D circle, a noun. The dynamic 3D verb has been projected into a static 2D noun, and its true nature is completely hidden.
All right, now let's use this framework. Let's start decompiling the world around us, from the tech in our hands to the very particles that make us up.
Take a computer chip. We see a transistor as this little physical thing, right? A noun. But its real identity, its essence, isn't the silicon. It's what it does. It's a verb. It's a stable little piece of geometry that exists to execute a rule. Either let electricity pass or block it. The object is just the hardware that runs the verb.
And this idea just blows up one of the oldest mysteries in physics, wave-particle duality. An electron isn't choosing to be a wave or a particle. It's always a single underlying process happening in a field. When we watch how it travels, we see a wave. That's the verb. But when we try to pin down its location, we see a particle. That's the noun. We're just looking at the exact same reality from 2 totally different perpendicular angles.
Now, this link between the verb and the noun, the wave and the particle, it's not just a nice metaphor. It's a law of geometry, which you could call the dual wave storage law. Think of it this way. The total reality of a system, we'll call it T, is made up of its 2 faces. You've got the dynamic verb, V, and you've got its static projected noun, which we're calling delta here. And this little equation, V squared plus delta squared equals T squared, it tells us they are locked together. Just like the sides of a right-angled triangle. You literally can't have one without the other. One is just a projection of the total reality seen from a different vantage point.
Okay, so we've got our new lens for looking at the universe. Now let's use it to hunt a ghost. We're going to point this thing at one of the 7 Millennium Prize problems in math, a beast called the Hodge Conjecture.
This is really the heart of the mystery. Deep inside these incredibly complex mathematical shapes, certain abstract features keep popping up. Think of them as echoes or vibrations that don't seem to have a physical source. It's exactly like hearing a perfectly clear, beautiful note in a piece of music, but there's no instrument anywhere that could possibly be playing it. A ghost note.
So, to put it really simply, the Hodge conjecture asks, does every single one of these ghost notes actually have a real instrument making the sound? Are the abstract ways of describing a shape always, and I mean always, perfectly anchored to the concrete physical parts of that same shape? Is the mathematical universe actually sane and consistent?
And here's where we can map this right onto our framework. On one side, you have topology. It's the study of abstract connections, of potential shape. That's our verb. On the other side, you have algebraic geometry, which studies the concrete shapes you can actually write down with equations. That's our noun. The whole million-dollar question is, does every possible verb in this world have a noun to go with it?
So, how does our whole verb-noun way of seeing reality solve this? How do we prove that there are no ghosts in the mathematical machine?
Well, the answer is kind of baked right into our very first rule. If the universe has to be a coherent, consistent system, then you just can't have effects without causes. A ghost note, that abstract feature, is an effect. It must have a cause. A topological echo has to have a geometric instrument playing it. The system literally demands it for everything to make sense.
So let's just walk through the logic. First, a mathematician spots one of these abstract holes, a ghost note. That's a potential verb, an echo in the system. But our rule says the universe can't have ghosts. It has to be coherent. So the mere existence of that abstract hole forces a real, concrete physical structure into existence to be its source. That structure is what's called an algebraic cycle. That's our material noun. It's the instrument. At that moment, the abstract and the concrete lock into phase. They're inseparable. And this final, balanced state, where every echo has a source, is called cohomological closure. The universe has balanced its books. No ghosts allowed.
And there it is, the profound solution. The Hodge conjecture isn't just probably true. In this framework, it has to be true. It's a basic law of how systems hold themselves together. You can't have the verb without the noun it creates. The ghost note and the instrument are really the same thing, just seen from two different angles.
Okay, let's zoom back out and just think about what this all really means. Because if this way of looking at things is right, it changes our entire relationship with reality.
The huge takeaway here is that this solid, stable world we see and touch every day, it isn't the fundamental layer of reality. It's more like the user interface. It's the clean, projected output from a much deeper, messier, more dynamic, cosmic computer that is running always just beneath the surface.
And that, right there, that's the ultimate quest. The great adventure of science and philosophy isn't just about cataloging all the things in the world, all the nouns. It's about figuring out how to decompile those static shadows back into the living, breathing code that's actually generating them. It's about seeing the verb hiding behind every single noun.
Which leaves us with one final, truly staggering thought. If we can learn to read the universe's source code, to really understand the fundamental verbs that write reality, what new nouns, what new kinds of worlds, what new possibilities could we learn to compile into existence? The story isn't just about reading the code anymore. It's about learning how to write it.